In this circuit, we have three resistors of different values connected in series. How do we know they are in series? Because they connected one after the other, forming just one path and not multiple paths. Let's perform a small activity now. Close the plug key and note the ammeter reading with these three resistors connected in series. Let it be I amperes. Next, place the ammeter somewhere between resistors R1 and R2 and note its reading. Similarly, place it between R2 and R3 and note the reading. What you will notice is that the current will be I amperes in each case. Yes, the current is constant at every point in the circuit. It tells us that in a series combination of resistors, the current flowing is the same throughout. Okay, now let's remove the ammeters which are between the resistors and try out something else. Now insert a voltmeter across the start of the first resistor and the end of the third resistor. Now plug the key and note the potential difference across the resistors. Let's say it's V volts. Now take out the plug key and disconnect the voltmeter. Now we insert 3 voltmeters in the circuit like this, one across each of the resistors. Now we plug the key and measure the potential difference across each of the resistors. You will notice that the potential difference across each of the resistors is different. Let's call them V1, V2 and V3 respectively. Even though the voltages are different, you will notice that the potential difference V will be equal to the sum of the potential differences V1, V2 and V3. This helps us derive something very important. Look at the entire circuit first. The potential difference is V volts and the current flowing through it is I amperes. Let's say these three resistors together form a resistance R ohms. We still don't know what R is, but we've just assumed all three together to provide a resistance of R ohms in this circuit. So according to Ohm's law, we can say that the V is equal to I times R. This was the entire circuit. Can you try applying the Ohm's law to each resistor separately? It's easy. For the first resistor, the potential difference is V1 volts. The current flowing through it is I amperes and the value of the resistance is R1 ohms. Applying the Ohm's law for the first resistor, we get V1 equal to I times R1. Similarly, for the other two resistors, we apply the Ohm's law to get two more equations. Now we can substitute the values of V, V1, V2, V3 in the first equation to get the result we need. V is I times R, V1 is I times R1, V2 is I times R2, and V3 is I times R3. Dividing both sides by I, we get the value of R as this. What did we just get? When two or more resistors are connected in series, the overall combined resistance R is the sum of the individual resistances. Now you understand why the resistance increases when resistors are connected in series. It's because each resistor when added in series adds up to the previous resistance. As the resistors are connected in series, we call the overall resistance Rs. On a new page, let's quickly review resistors in series. Take this simple electric circuit with one resistor. What will happen if I add more resistors in series? The overall resistance will increase and the current in the circuit will decrease. The current flowing in the circuit will be the same at every point in the circuit. And the overall resistance will be the sum of the individual resistances. In the next lesson, we will solve interesting problems related to resistors connected in series.
Resistors in parallel. Now let us see the parallel arrangement of resistors. Take three resistors, say R1, R2 and R3, and ammeter, voltmeter, battery, plug key. Connect three resistors R1, R2 and R3 in parallel to each other in the circuit with battery, plug key and ammeter. Connect voltmeter in parallel with a combination of resistors. Plug the key and note the ammeter reading I and voltmeter reading V. Take out the plug from the key. Remove the ammeter and voltmeter from the circuit. Connect the voltmeter across each resistor and insert the ammeter in series with the resistor R1. Note the ammeter reading I1. Similarly, connect voltmeter and ammeter with other two resistors I2 and I3. We can say that the total current in the circuit I is equals to sum of currents I1, I2 and I3 through resistors. By applying the Ohm's law to the parallel combination of resistors, we have I equals to V by Rp. Now applying the Ohm's law to each resistor, we have I1 is equal to V by R1, I2 is equal to V by R2 and I3 is equal to V by R3. Substituting 1, 2, 3 and 4 in B, we get V by Rp is equal to V by R1 plus V by R2 plus V by R3, or 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3. We may conclude that the reciprocal of resistance Rp is equals to sum of the reciprocals of individual resistances.
We can monitor and control the heat generated by electric current by regulating the current supplied to an appliance. James Prescott Joule, a British physicist, expressed the relationship between the heat generated in a conductor and the amount of current flowing through it. This relationship is popularly known as Joule's law or Joule effect. Joule's law states that the amount of heat produced in a conductor is equal to the product of the amount of current squared, the resistance of the conductor, the time for which the current passes through the conductor. To derive Joule's law, let a potential difference of V volts drive a charge Q coulomb through a heating element, and W be the work done. The potential difference is a measure of work done in moving a unit charge across a circuit. From this, we get equation 1. V is equal to W divided by Q, or W is equal to VQ. The amount of electric current passing through a circuit is the product of the rate of electric current and the time of flow. From this, we get equation 2. I is equal to Q divided by T, or Q is equal to IT. Substituting the value of Q in equation 1, we get equation 3. W is equal to VIT. Now let's use Ohm's law. V is equal to IR. In expression 3, to get the formula for the total work done by electric current. The total work done by electric current, W, is equal to I square RT. This work done by electric current to overcome the resistance of a conductor is converted into heat energy, which is represented by H. Hence, H is equal to I square RT.
In this video, we will understand heating effect of current. We know that a battery or a cell is a source of electrical energy. The chemical reaction within the cell generates the potential difference between its two terminals. This potential difference sets the electrons in motion to flow the current through a resistor connected to the battery. In an electric circuit, every component offers resistance to the current. But an electric component, which offer a specific value of resistance, is considered as a resistor. When electrons flows within the resistor, they collide with the atoms of the resistor. And because of that, atom starts to vibrate. More the collision, more atoms vibrates about their mean position. This vibratory motion of atoms generates heat energy within the resistor. And hence, temperature of the resistor increases. This phenomenon is known as heating effect of current. Heat can be represented as. This is known as Joule's law of heating, where H is heat, I is current, R is resistance, and T is time. The law implies that heat produced in a resistor is directly proportional to the square of current for a given resistance. Directly proportional to resistance for a given current. Directly proportional to the time for which the current flows through the resistor.
Electric appliances convert electricity into heat energy, providing you energy in a form that you can use. In this lesson, you will learn how electrical energy transforms into heat energy. At the end of this lesson, you will be able to describe the heating effect of electricity, identify the cause of the heating effect of electricity, illustrate the working of an electric fuse, state and derive Joule's law. When you switch on a bulb, the thin metallic wire or filament in the bulb turns red and the bulb starts glowing. This is because when an electric current passes through a metallic conductor, the conductor gets heated. Thus, electrical energy is transformed into heat energy. This is called the heating effect of electricity. Many appliances in our household utilize the heating effect of electricity. Some common examples are electric irons, room heaters, and storage water heaters. Conductors used in electrical heating appliances to convert electrical energy into heat are called heating elements. For example, the filament in a bulb is a heating element. A good heating element should have high resistivity so that it gets heated quickly, high melting point to enable it to withstand high temperature, negligible variation in resistance due to temperature changes. Three metal alloys most commonly used as heating elements are nichrome, an alloy composed of 80% nickel and 20% chromium; manganene, which is 86% copper, 12% manganese and 2% nickel; constantan, a copper-nickel alloy with 60% copper and 40% nickel. If your electrical appliances receive very weak or very strong current, they could be damaged and stop functioning. To prevent such damage from fluctuations in the current, an electric fuse is used in the circuits of most houses these days. An electric fuse is a safety device used to protect an electric circuit against excessive current. The mechanism of the electric fuse is based on the heating effect of electricity. You may have often heard people talking about replacing the fuse in their homes because the fuse blew, cutting off the power supply. An electric fuse contains a fuse wire. that is designed to withstand a particular amount of electricity flowing through it. When the electric supply fluctuates and the current becomes too strong for the wire, it melts and breaks the supply of electricity. Electric fuses are rated according to the current that they can withstand. For example, a fuse rated 5 ampere can withstand current flow to the maximum of 5 ampere. If the current flowing through that circuit exceeds 5 ampere, the fuse wire melts from the heat, cutting off the power supply through that circuit.
Have you ever bought a bulb from a hardware shop? The shopkeeper asks you which bulb you want and you say, give me a 100-watt bulb or a 60-watt bulb. But what does this 100-watt or 60-watt mean? Have you ever looked at electrical appliances in your home carefully? If you have ever looked at iron in your house, it has 1 kilowatt written on it. In the same way, 1.5 kilowatt on the heater as well. But what is this watt or kilowatt? This is actually the electric power of this device. Now what is this power? Let us understand about this. The rate of doing any work is called power. For example, if you take 10 minutes to get home from school, in coming home from school, your body must have done some work. The rate of work done by the body in those 10 minutes can be shown as power. In terms of science, the work done is equal to energy. If its rate is taken, then it represents power. Like heat, power can be written in different ways. SI unit of power is watt, which is represented by W. 1 watt is equal to 1 joules of work done in 1 second. Let's go back where we started 100 watt. 100 watt means that the bulb will consume 100 joules of energy in 1 second. Let's take another example. Your homes must have electricity meters. You must have heard that 50 units of electricity have run this time. Do you know what these 50 units are? Let us understand this. 1 unit means 1 kilowatt hour. We use kilowatt because watt is a very small unit. 1 kilowatt is equal to 1000 watt. Here watt hour is the unit of electrical energy coming to our houses. 1 watt hour is the electrical energy consumed when 1 watt power is used for 1 hour. The commercial unit of electrical energy is kilowatt hour and it is commonly known as unit. 1 kilowatt hour is equal to 3.6 into 10 to the power 6 joules.